Right. Where we were was that we were about to start talking about the second law. And one thing I just thought that maybe I should, the first law involved fair amount of issues like the maxi issues, namely perfect differentials. So just spend a couple of minutes before I start out on the second law, that this, for example, if my question is that if I have dz, which is x dy plus y dx, is that a perfect differential? So this is a question for you, that if I write dz as x dy plus y dx, is that a perfect differential?
It can be or cannot be. If x equals to dz by dy, then only it is a perfect differential.
So it's a perfect differential, right? Because I can go ahead and write this as d of xy. So that's what, but suppose I have dz equal to x dy minus y dx. Is that a perfect differential?
No, sir.
No. All right. So can I make it a perfect differential? What would I? So it is correct that it is not. So immediately the question would be that how can I make it a perfect differential? And that is the sort of thing that you should sort of be familiar with, that it's all, you look at this and it is, you can immediately recognize over here, it is, you do see that we have it's not a perfect differential as such. And so a question is whether something like this can be made into what would be an integrating factor, how does one go about it? So a little bit of practice on that would be good for you. I will request Shaurabh, who takes the tutorial, to talk about a bit on perfect differentials, so that you are comfortable with it as we go along. So a little bit of practice on perfect differentials would be a good thing. So, all right. So the obvious one you do recognize, the other one you do recognize it is not, but then question is how. And so because we will encounter the perfect differential once more, not immediately, but after your mid-semesters, we will be talking about perfect, at least one bit of issue which would require a perfect differential. So anyway, these perfect differentials, what I was after really is that should be something which you are familiar with. Somewhat familiar, I mean, all right, so on to the second law, and the question is, it has to, this is what actually started off thermodynamics, the Carnot's work, which talked about efficiency, the process which is called engine, the cyclic, and which operates on a cyclic business. So engines and refrigerators and things like that, that is what one has to worry about. So, all right. So what we would be doing for the most part is something which is very idealized, but at certain points, a little bit of touch with reality we would try to bring in. All right. So the statements which of the second law are attributed to Kelvin, and who said that it is impossible to extract heat from a reservoir at constant temperature and convert it completely to work. So that was the Kelvin statement. Now, the important word is a reservoir. What's a reservoir? It's something from which you can draw heat. That is a reservoir. A reservoir is something from which you should be able to, it's a reservoir of heat. And you can somehow draw heat from it. And the point is that in the process, all these ideal reservoirs which the second law is concerned with, in the process there is no change in temperature. That obviously sounds a little strange, but the practical meaning of it is that it is a huge source of heat, so that, I mean, for example, it is a large water body. So water bodies, I mean, can be a very good source of, and also a sink of heat, simply because that the specific heat of water is large, and the large mass, if you take away some heat from it, certainly the relation delta Q equal to mass times specific heat times delta T would be operational. But if this is large and this is large, which it is for water, then the delta T is going to be very small. So that is the meaning, practical meaning of a reservoir, that it is large system of rather high specific heat, from which you are drawing heat. The the consequent change in temperature is essentially negligible. So that is what a reservoir is. So, all right.
So, some people are waiting.
Pardon? Somebody is waiting. All right. Okay. So that's statement number one. And then there was the alternative statement due to Clausius. And that says that it is impossible to extract heat from a reservoir at a lower temperature and deliver it totally to a reservoir at a higher temperature. So that's the Clausius statement. Both are negative statements. You can't do this or you can't do that. So you can't extract heat from a reservoir and convert it completely to work. You can't take heat from a reservoir at a low temperature and deliver it completely to a reservoir at a higher temperature. Always the meaning of these transitions is that what is underlying these transitions, the word totally over here or completely over here, these words essentially mean that no change is happening anywhere else. So that is what the meaning of this totally or completely is. That is the only final thing that has happened, is that I have taken heat from a reservoir and converted that heat into work. That has not affected anybody else except that reservoir that we are talking about, from which has lost some heat, and there is some mechanism which has benefited from this conversion of heat to work. Apart from that, the rest of the universe just does not know anything about it. Similarly, with the Clausius statement, from the lower knows that you have moved some heat out of it, and the upper higher temperature reservoir knows that you have delivered some heat to it. Apart from that, no change has happened anywhere else. So this is what the implication of these words like completely, totally, and so on and so forth are, that nothing except the process described has taken place. So given that you have two statements of the second law, it is imperative that they have to be the same statements. So these two are required to be identical. So the first, because otherwise you don't know what the second law is. So if they are to be identical, the way of proving that they are identical is that you assume. So how do you prove they are? The method of proof is assume K wrong, then show that C is wrong. So if K is wrong, then C is wrong, and then assume C is wrong, and then show K is wrong. So then that sort of makes it clear that we are talking about the same thing. If one of them gets, if the Kelvin statement is violated, then immediately the Clausius is violated. If the Clausius is violated, then immediately the Kelvin is violated. So they are talking about the same thing. So if you happen to violate one, you happen to violate the other as well. So all that I need to do is talk about only one of them. And given these two statements, I can go about using any one of them as it suits me. So that's the great advantage. Having these two statements, they are equivalent. And if you are going to rule out a process as being unphysical, you can either use Kelvin or you use Clausius, and your job is done. So it has practical benefit. So having these Y for ages, I mean, one should be working with two statements of the same law. That should bother you. I mean, you don't do that with Newton's law. I mean, somebody doesn't come and say Newton's law could be stated in this other manner as well. That doesn't happen. But here it has historically been true. And I mean, 150 plus years later, we still talk about it. Textbooks write it in this way. And it's actually just practically useful. I mean, when one deals with practical thermodynamics and certain processes are feasible and certain others are not feasible, you can use any one of these arguments to test the feasibility. And so it has practical benefit, and that is why one holds on to these two different statements. But it is imperative that you show that they are the same. All right. So now showing that they are the same is not so, that is, showing requires, everything requires its own language, and showing this requires the language which is useful. And that language which is useful to show is the language of heat engines and refrigerators. So the language has to be set. I need to define what engine is. So what an engine does is, so that's the definition of an engine. It takes a heat reservoir and extracts a certain amount of work Q1 from it. A heat, so from a reservoir at temperature T1, this engine extracts a certain amount of work, heat Q1. And then what it does is that it goes to the actual operation where this work Q1 is converted to work. And as Kelvin says, not all of it can be. And there is the rest, which is dumped to a lower temperature reservoir, which is a reservoir at temperature T2, which is less than T1. So this is an engine, as we said, and that is the schematic picture of an engine: a reservoir at temperature T1, a reservoir at temperature T2, and they always stay at T1 and T2. You extract a certain amount of heat Q1 from it without changing its temperature, because that's the definition of the reservoir, and you can convert it to work, but not all of it can be converted, says the second law, and you dump the rest to this lower temperature reservoir, which is T2. It gets the amount of heat Q2, but does not change its temperature, once again by definition of the reservoir. So that's your, the engine in practice looks far more complicated. Obviously, I mean, it requires, the actual engine actually requires some pump to do this work for you and get some, the pump operates to actually, there is some heat reservoir, which is some kind of a furnace. From the furnace, you have this next step where you use a boiler, for example, and from the furnace to the boiler. Boiler is the one which is at temperature T1, and the heat from the boiler, you may use it to operate a pump, which, I mean, what you have to do some work. So what the pump does is actually drives a turbine. So this is a turbine which gets driven. So the pump extracts heat from this boiler over here, does some work, and that is the work which, I mean, the pump puts in its own 2 bits, and you get the observed work, which is the rotating the turbine. And then there is this lower temperature reservoir over here, where the heat is rejected, the pump drawing some heat from the boiler, rejecting some heat to a lower temperature, which eventually connects up to some water body and dumps the heat over there. So when there is this process of extracting work, I mean, the work is done in actually rotating some machinery or other, but obviously the heat produced by the furnace is going to go to a boiler, and there has to be a pump. So all sorts, a lot of complicated machinery in the process, replaced by a diagram which is this, where you see a heat drawn and which is amount Q1, drives the gets converted to work, and then dumps it into a lower temperature reservoir. So the engine that you see, which we will be drawing and all the textbooks draw, are sort of idealized version of what actually goes on in a typical production unit. So this is our engine, and the typical engine is typical example is your car engine. So typical is the car engine, and what eventually gets done, as you can see, the last bit of thing is you dump heat in the surroundings, and that is what the these emission norms and so on and so forth, which one is rather concerned about, comes in. So that is the emission which one is worrying about, and it goes into, as I said, the water bodies, and therefore this is the part of the thing which contributes to global warming. So this connects up with what I said in the our idealized situation seems to be that the temperature does not change. The water and the idealization is that the water body is so huge that if I add a finite amount of heat to it, the temperature would not change. But if you do this over hundreds of years, you are going to run into a problem, which is because eventually it is, after all, a finite amount of water body, and everybody is dumping their heat into it, and the temperature has to change. So the engine, this dumping business is what is related to the global warming.
Sir, for car engine, there is no water body to eject the heat.
Huh?
For cars or motorbikes, they don't have any water bodies to eject the heat. So why they eject their heat, excess heat?
What doesn't have water bodies?
The car engines, they don't have water bodies to eject the extra heat.
See, there has to be some kind of reservoir which, I mean, you can just expel it to the atmosphere. So you need not have a water body as the only emission. I mean, obviously the cars are not putting it into they are putting it into the atmosphere, not to a water body. But the nuclear plants, for example, would put it in the water body. So it's a question of whether it is, you can put out the heat to the atmosphere, which is once again a huge reservoir. Or, I mean, when it is, when these factories are concerned, the factories are generally the output which eventually goes into some kind of a water body or other. So the other is the reverse of the engine is the refrigerator. So the refrigerator, you now extract heat from the low temperature reservoir. So the low temperature reservoir, you get the heat extracted from there, and a certain amount Q1, Q2, let's say. So Q2, which you extract from there, and now you have an engine which gets to work, and this work which takes the heat which you get from this temperature T2, the work what this machinery does is takes this heat Q2 along with the work that it does and deposits Q1 equal to Q2 plus W to reservoir, which for your refrigerator you can see the back side of the refrigerator is hot, and the heating that this dumping of heat by the in the refrigeration cycle is what heats up the backs of the refrigerator. The new designs, you will find that they keep the back of the refrigerator somewhat not so hot as the refrigerators of 20 years ago, because they have a way of actually dissipating this heat into the atmosphere in a by a more sophisticated process. So if you touch the backside of the refrigerators these days, it's not as hot as it used to be 20 years ago. But basically, I mean, all right, that's the refrigerator. So, all right. So these are the two things. I mean, our whole business was to talk about Clausius and Kelvin. And in the process, I need these two things for the second law, engine and a refrigerator. So it's the, and while we are at it, we can also define the efficiency as 1 minus Q2 over Q1. So Q2, the first law, conservation, Q1 has to be W plus Q2. So Q1, so this is W, the amount of work that you are getting from it. So how much of Q1 has been converted to useful work? So it is W. And what is W? That is the first law, the conservation business over here. Heat and work. The conservation law requires both of them to be present. And so Q1 is equal to W plus Q2. And that's what allows you to write this as 1 minus Q2 over Q1. So that's the efficiency of the refrigerator engine or the refrigerator, as the case may be. So here it is. I mean, that's that. And now we can get to work on so it says, so we start with Kelvin, and which says that it is not possible to extract. So we have this reservoir at temperature T1, and I extract an amount of heat Q1 and take an engine and convert it all to work. So Kelvin violated. I have from a reservoir at temperature T1, I have extracted a certain amount of heat Q1 and I have converted it completely to work. This is what Kelvin said I would not be able to do. And this is precisely, let's say, what we have done. So what we now do is take a reservoir at a lower temperature T2 and extract certain amount and so this was an engine, and now essentially I want to run a refrigerator. So I take an amount of heat Q2 from here, take this W and put it back. So it's Clausius would come into play now. So I have taken temperature T2 less than T1, extracted some heat from there, which is the amount Q2, and I have taken this W, and I have taken W plus Q2 and dumped it into the reservoir, which is the T1. So I have taken, what has happened is that at the end of the day, you have got this work done over, you have taken this, which is Q1, and you have dumped Q1 plus Q2 over here. So this is equal to Q1 plus Q2, because that was W. So Q1 plus Q2 has been dumped into T1. Q1 was extracted from T1. So at the end of the day, Q2 has been deposited, Q2 has been deposited in T1. So when everything is said and done, what has happened? You have extracted the amount of heat from Q2, which is at a lower temperature T2, and transferred it completely to a reservoir which is at a higher temperature T1. So this violates, Kelvin has been violated, and Q2 goes from T2 to T1 with no change elsewhere, and it is Kelvin, Clausius has been violated. So that's that while Kelvin violated leads to, you can arrange a setup so that if Kelvin can be violated, you have Clausius, which is violated. So now it is Clausius which is violated, and you start with a reservoir which is at a lower temperature T2, and run a refrigerator, let's say, which takes the run nothing, let's not even worry about it. I extract a certain amount Q from here, set it into Q2 over there. So it's T1, which is greater than T2. I violated Clausius by some mechanism or other. I have taken a certain amount of heat Q2 from here and deposited the same Q2 at a reservoir, which is at a temperature Q2. So, all right, now what I can do is I can take this Q2 from over here. So I take this Q2 from over here, run an engine which does a certain amount of work W and deposits Q2 minus W to this T2 over here. So I take this, so I've deposited I have violated Clausius, taken Q2 from T2 and deposited into Q2, which is which is at a reservoir, which is at a temperature T1 greater than T2. And then I run a heat engine now between T1 and T2. So here is my engine extracting this whole Q2 from here and carrying out a certain amount of work and depositing the rest over here. So when at the end of the day, what have I done? I have taken Q2 out of here. I have deposited Q2 minus W here. So net heat leaving T2 reservoir is Q2. Nothing has happened in the reservoir T1, no change. And how much work has been done? Work done is Q2. So you have engineered a process whereby you have drawn a certain amount of heat from a reservoir at the constant temperature and converted it entirely into work. So that is Kelvin violated, and therefore Clausius violation leads to Kelvin violation, and Kelvin violation violates Clausius. Consequently, the two statements are identical. So this comes, so we have the second law in two different forms, and the two forms are actually so I have my basic engine then. So basic engine is something which takes a certain amount of draws a Q1 amount of heat from a reservoir at temperature T1, does a certain amount of work W, and dumps Q2, which is Q1 minus W to this. That is my basic engine. So what is the efficiency of this engine? So efficiency is eta. Your idea of the engine is take heat and convert it into work. So the efficiency has to... So sorry, what's the crosstalk?
No, sir, I think he's unmuted by chance. Maitreya, please mute yourself.
Huh?
Sir, someone got unmuted, I think. Yes, sir, now it is okay.
Okay. So the efficiency is the amount of work that I have done and divided by the amount of heat that I have drawn from the fraction that is the efficiency of the engine. So that is the efficiency of the engine over here. And now comes the whole idea is that I want the efficiency to be eta has to be maximized. That so eta has to be maximized is the goal. So this whole business of the second law of thermodynamics is that you have a statement that if I run a heat engine, its efficiency is going to be defined as not all heat can be converted to work. So there is an efficiency which is given by this. And my goal is to maximize that efficiency, and W is Q1 minus Q2 over Q1. So the efficiency is 1 minus Q2 over Q1. So that's the efficiency, and one has to play with that. So that's what. Now comes a new feature, that what is what's called a reversible engine. So the reversible engine essentially is something that if I can perform this operation over here, the reversible engine would be capable of performing the process, which is pick up heat Q2 from T2, and take W and deposit Q2 plus W to T1. So that's the reverse cycle. So engine which can do both, that is, extract heat from over here, a certain Q1, and then deposit heat Q2 to this over here and get can also, if it is capable of running in the reverse order, that is extracting Q2 from here, using a certain amount of work W and depositing the thing here, resultant heat to T1, that is somebody who can do this as well as the reverse process, is a reversible engine. And the point why are reversible engines so useful? The reversible, why does one want to talk about reversible engines? Because the reversible engines have a very nice property. All right. Now, this nice property, before what is a desirable property to have? This is an eta. The efficiency is 1 minus Q2 over Q1. Now, the engine means that I have a working substance. I mean, obviously, there is some setup which essentially can determine, I mean, whether you are using a typical engine would be what Carnot imagined. So let's work with this question of working substance. So let's clarify what a working substance is going to be. Why a working substance? So working substance, you imagine gas is the working substance. So any kind of a gas. And you imagine this process. The process being, so on the PV diagram, so the gas is initially over here at some temperature T1. And what you do is you isothermally expand that gas. So here is isothermal. So this is now Carnot entering, this is history going backwards and forwards. The arguments which I just gave you were the arguments of the 1850s, Kelvin, Clausius, all people of that era. And now you go back a little bit to Carnot, who was actually an engineer, and the whole business for Carnot was to get something going. I mean, actually convert heat to work. So there would be a working substance. So a working substance is the easiest working substance was a gas, right? So what Carnot envisaged is that you expand, let the gas expand, you heat it, and it expands. Let's say you arrange an isothermal expansion. So that is a reservoir at constant temperature T1. So it has expanded from here to here, and then you switch off, don't let any heat exchange to take place. And in this process over here, you see the work is getting done, because we have learned that W is equal to integral PdV. So W is equal to integral PdV. So there is work done along this cycle over here. There is also Q, which is equal to W along that cycle, because it's the first law told us that dq is equal to d. So assuming that temperature change means that the internal energy is not changing, Q is W along this path over here. So it's an isothermal path. And I know how much work has been done, and that work is being done by putting in a certain amount of heat into the system. So I have put in a certain amount of heat Q1 over here, and now I let it expand without any heat exchange. So no heat exchange with the system, and it expands a little more. So this is the adiabatic expansion. Still doing work. I mean, it's still doing work over here. And this work means that its temperature is going to change now. So its temperature, which was T1 here is this adiabatic expansion. And then its temperature has to change, because the first law told you that if dq is equal to 0, then the internal energy, what the work done would do is change the internal energy. So the internal energy changes over here, and the system cools to this T2 over temperature T2, and then you need a cyclic process, because if it is going to be an engine with this efficiency eta equal to 1 minus Q2 over Q1. So if I'm going to have this efficiency, one stroke is simply useless. So if I have to get things going, get actually useful work out of it, I have to go on doing it repeatedly. So one stroke simply gets me this small amount of work W, but then I go on doing it. So it has to be a cyclic process. Get the system back to where it started and let it go again. So that's why the next step which Carnot envisaged was at this step, I compress the gas. So I compress the gas over here. So it expanded isothermally, it expanded adiabatically, and now it is compressed isothermally at T2, and finally allowed to come back here through another. So here is this isothermal process in which a certain amount of heat Q2 is given out to the surroundings, because now it is a question of compressing it. So W is negative, dq is negative, so heat leaving the system over here, and that. And therefore, so heat Q1 taken in here, heat Q2 lost, no heat exchange over here, and this is at temperature T1, this is happening at a temperature T2. So that is the Carnot cycle. And so that is your Carnot cycle, and this reversible engine has the property that I use the language of a gas, and now this is among the gases, there could be this gas, that gas, or some other, or instead of a gas, it could be some kind of a liquid. I mean, you would be using some kind of a liquid, for example, or you use some other substance. But the important issue with the reversible engine is that the reversible engine efficiency is independent of the working substance. So with a reversible engine, you have the result that its efficiency is independent of the working substance, and therefore the reversible engines are sort of universal, and hence when you talk about things, for the most part, one talks only about reversible processes. So it is reversible engines which one talks about. You are making, which you must realize that you are making a tremendous approximation. We have gone through this question of reversible. Reversible has to be done ever so slowly. So at every point of the reversible process, equilibrium is obtained, and systems, and you can use the ideal gas law when it is a gas as PV equal to RT to be valid at every point of the process. That is what is the characteristic of a reversible process. And what one is saying is that if I have a reversible engine, it is very important that I have a reversible engine, because then the efficiency is actually independent of the working substance. So here is this is where the importance of a reversible engine comes in. So you have to realize reversible engine is an idealization, and therefore efficiencies which you calculate on the basis of the reversible engine is not the efficiency that you will see in real life. So what we will talk about one particular situation where you can, a model where you can actually calculate a real life efficiency, and we'll see how it goes. So hopefully next Thursday I would be able to do that. So so efficiency, and so how do I know that so then comes the question, how do I know this result, that the efficiency is independent of the working substance? So I consider two so it is a reversible engine, and a reversible engine which is being considered, and a reversible engine between working between temperature T1 and T2. So here we are. So takes in an amount of heat Q1, rejects an amount of heat Q2. This is at temperature T2 over here. So I come, sorry. So I take a working substance 1. So this is working substance 1. And it's a reversible engine, and I run it in this fashion over here. That it is this, it draws in a certain amount of heat Q1, it takes in, rejects heat Q2, and delivers the amount of work, which is Q1 minus Q2. I take another working substance, and let's say for that, so I take a different substance 1, and now it's substance 2, and at temperature T1, it draws in Q1, goes like this, and like this over here, and that, and it rejects Q2 prime and does a certain amount of work W prime, which is Q1 minus 2. So this is substance 1 doing this, substance 2 doing this. So what do I want to do? What I want to do, so this is this PV curve. I want to consider a combined operation of these two cycles, combined operation with substance 2 running in reverse. The efficiency eta of this engine is 1 minus Q2 by Q1. The efficiency eta prime of this engine is 1 minus Q2 prime over Q1. So these are two reversible engines. But they are using different substances, and with substance 1, the efficiency is this, and with substance 2, the efficiency is this eta prime. Now I want to do a combined operation of these two cycles, over here, where I'm going to have a combined the substance 2 is going to run in reverse. That is, I take in Q2 prime over here, put in an amount of work W prime and reject the Q2 prime plus W prime over there. So I have a situation where you are going to see that, so what do I have at what I have over here in this combined operation, you are going to have amount of heat which at T1, the amount of heat which you have drawn from T1 is Q1 minus Q1 prime. So the combined operation, there I'm drawing it on the same PV plane. At the temperature T1, it was drawing Q1 and it is now rejecting Q. This one is rejecting Q1 prime. So the basic thing is that I have, so the net thing is that I have drawn Q1 minus Q1 prime. How much have I rejected? I'm rejected Q2 minus Q2 prime. How much work I have done? The work which I have done is Q1 minus Q2 prime, and then it is the minus of Q1 prime minus Q2 prime. So my net heat in Q1 minus Q1 prime, net heat out Q2 minus Q1 prime, and then this is. So W is set Q1 equal to Q1 prime. So let's take Q1 equal to Q1 prime, and then this operation says that the amount of work done is Q2 prime minus Q2. So W equal to Q2 prime minus Q2, that's the amount of work that is being done, and how much heat, no heat transfer over here. So how much heat has dumped into the work done is Q2 minus Q prime, and the amount of heat leaving T2. So amount of heat leaving T2 is, this is Q2 prime which has been reversed, is Q2 prime minus Q2. So this is the amount of heat leaving T2, and this is the amount of work which is being done. This is not possible with Q. So Q2 prime greater than Q2, not possible. So the conclusion is that if the thing is, I'm drawing a certain amount of heat Q2 prime from minus Q2, if I draw that amount of heat from reservoir 2 and convert it to work, which is say entirely to work, that is ruled out by the Kelvin statement. And unless you say, it is Q2 prime is less than Q2, and then it is not a question, then nothing is relevant. But if I say that Q2 prime is greater than Q2, then I have taken an amount of heat from a reservoir at temperature T2 and converted it completely into work. So Q2 prime greater than Q2 is not possible. And now I can, so that's one kind of where I ran this in ran this forward and ran that backward. And now I can reverse the whole thing. The next thing I will do is consider 2 running forward and 1 backward. So then you just reverse it. That Q2 and 2 is running forward and 1 is running backward, and that will immediately, if I repeat the same argument which I did over here, then it will now work out that Q2 prime less than Q2 is not possible. That is, Q2 greater than Q2 prime not possible. I mean, I'm not going through that argument because it should be all right. Even if either it is obvious to you or if it is not obvious, you can just go through the argument which I went through over here, and the net result has to be that just as Q2 prime greater than Q2 was not possible if I ran this forward and this backward, if I reverse it running this forward and that backward, and then under the same situation, Q1 equal to Q1 prime, it would be Q2 greater than Q2 prime would not be possible. Therefore, if neither is possible, then Q2 has to be equal to Q2 prime and Q1 has to be equal to Q1 prime. And therefore, the efficiency of this, so Q2 equals Q2 prime, Q1 equals Q1 prime, eta is equal to eta prime, and the efficiency of the reversible engine is independent of the working substance. That is certainly the most interesting feature of this engine business, that the second law of business you talk about engines and so on and so forth. It looks for a while like you have lost a sense of the physics. But here is where the physical arguments make a very strong comeback, that if it is a reversible engine that I'm talking about, it simply does not matter what my working substance is. So for a reversible Carnot engine, all substances are the same. You get the same efficiency for whatever substance in use, and therefore I will use an ideal gas. You see the logic? I mean, that you just don't, write down that the efficiency is 1 minus Q2 over Q1 and simply go use a fantasy of the ideal gas and calculate efficiency and say that is the efficiency of the engine. No. You go through it the very hard way. You prove that if it is a reversible process that I'm talking about, if it is a reversible engine, then the efficiency is independent of what is the working substance. And then I say, look, in that case, the ideal gas is relevant. I will calculate the efficiency with an ideal gas as the working substance. So it's, you must have seen thermodynamics. This is not the first time you are seeing thermodynamics. So you are certainly familiar with all this. But there are certain points which I would like to emphasize if you have not worried about these things. And one is this question of that, why is it possible for me to get away using doing calculations with an ideal gas? So ideal gas is an admissible substance for an engine. I mean, look, your car engine is not using any stupid ideal gas. But the point is that, of course, I mean, it is neither this reversible engine. Anyway,
I have a question.
That story would have to come a bit later. Yeah, what?
So, when we are considering the first case, like, can't it just follow from that Q2 greater than Q2 prime is not possible, because if Q2 is greater than Q2 prime, then it is taking heat. It is taking heat, and then a work is being done on that system, but it is not losing heat. So that violates that Clausius statement, right? That so it can just follow from the first case.
No, what follows from the first law?
So I'm asking that do we need to consider the second case, like 2 running forwards and 1 running backward? Because when we are considering the first case, can't it just follow that Q2 greater than Q2 prime is not possible?
But the first case has simply told me that Q2 has to be greater than Q2 prime. So that's with the engine, with this first engine running forward, second engine running backward, I have simply said that all that I've got, that Q2 greater than Q2, Q2 prime greater than Q2 is not possible. So, I mean, the first law cannot enter simply because that these issues, I mean, you don't know how to calculate with the first law until and unless I actually give you a equation of state. You have the first law is not functional, right? I mean,
that's fine. Like, I'm asking that, in this first case, if I take Q2 greater than Q2 prime, then that means that work is being done into the system, and then it is releasing some heat, but it is not it is not extracting heat from any system. So it violates that Clausius statement, doesn't it?
No, because the first law is simply saying that delta Q is there is the internal energy for me to worry about, right? I mean, the first law has this internal energy in it, and I don't know what the internal energy of a particular substance is. So if it was that I could argue that delta Q is delta W always, then I could use the first law and not do the reverse process. But that is, I don't have that luxury. Na? I mean, I have that luxury only after I have established that, look, I mean, you can do it for anybody, and therefore you can, I mean, do it for an ideal gas. And therefore, I mean, the argument about the delta U, which would be valid. But before that, I don't know. I mean, that what would happen, the delta Q equal to delta U plus delta W leaves me with the delta U, which can cover up everything else, right? I mean, on which I have no handle. So that is why it is important to do it without resorting to the first law. I mean, first law has this delta U on which I don't have a handle. And this argument is telling you that, look, you don't need to do that. you simply reverse this argument, get into a contradiction, and then say that, look, I mean, it is independent of the substance. That's the way I would look at it.
Yes, I got it.
So great. I mean, it's independent of substance, and therefore I can use ideal gas to calculate it. And so this ideal gas, all right, I should be able to finish it off, the ideal gas answer, unless I make an error in a few minutes. So it's, sorry, let's get all this out of the way. So here is now the process, PV process. This is with the ideal gas. This is at a temperature T1. Here is P1, V1, and here is P2, V2, and then some P3, V3, and then P4, V4. And this is my V, and this is my P. This is a isothermal, this and that. This is adiabatic, and we are. But now I know that PV is equal to nRT. So n is the number of moles. We can just. So I know the relation between this is ideal gas, and I have a ideal gas law to help me through. So here is now the your isothermal thing, where you can do you can calculate the dW is equal to PdV, du is equal to 0. So W dq is equal to integral PdV. So this is the total amount of heat in, which is equal to, so P is, so it is RT1, and it is log V2 over V1. So V2 over V1, so that is integral Q. So Qn is equal to integral dq. So here is my Q1, the amount of heat coming in, which is so now what is Q out? Q out is what is going on over here, and Q out is the same thing, integral PdV, but now it is RT2, and it is at log, you have gone from done V3 over V4. So Q in, Q out. So that is the efficiency eta is equal to 1 minus Q2 over Q1. So I need this ratio. So the ratio is this Q out, which is the Q2, Q in, which is Q1. And the ratio is T1 by T2, but then there are these logs which I have to, log of V2 over V1. So I need to show that V2 by V1 is V3 by V4. So for that, you need to worry about the adiabatic process that is going on over here. Now the point is that I need to make use of P1 V1 is equal to P2 V2, and then it is P2 V2 to the power gamma. This is getting out of time. Sorry, I'll P2 V2 to the power gamma is this is this, and then it is P3 V3 is equal to P4 V4, and then P4 V4 to the power gamma is P1 V1 to the power gamma. right? I mean, so this. So you have this process for that, and you can make use of this to just judiciously, along with the PV equal to RT wherever applicable, the thing which you would be able to show that V2, what you need to show is V2 over V1 equal to V3 over V4. So judicious use of these over here, along with the fact that P1 V1 is R times T1. So the yeah. So that this is all right. I mean, it's a question of all of these RT1 and P2 V2 is RT2. Taking just looking at them and taking dividing one by the other would get you into this relation where V3 over V4, V2 over V1, that is essentially dividing this by this over here and dividing the other by V3 over V4 over here should get you the answer. If you you might run in, we'll complete it next time. Takes a couple of minutes to do, but this is what you will find. You can at least, I mean, give it a try and see, and eventually the efficiency should become 1 minus T2 over T. So that is the efficiency of the Carnot engine. So just go through the algebra a bit, and if you, I'll take the few minutes to do it next time if you are stuck anywhere. So anyway, so that's that. We have we are actually covered quite a bit, and all right. So we'll see where now what the applications of this where this takes us next time. So all right.
Recording stopped.